Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this lecture. Today we will start a new topic, groups. The group structure is a very important structure in algebra, and we will discuss groups, its properties and many related definitions and results. So, what is a group? So, we know what is a set. So, group means it is a set G together with an operation, a binary operation. Let us call it star. Okay. So, this pair is called a group. Now, this pair is called a group if they satisfy certain properties, okay, and we will define them. But first of all, star is a binary operation. What does it mean? It means that it takes two arguments. So, like multiplication is a binary operation, addition is a binary operation. So, if you take two elements G1 and G2 from the set G, then G1 star and G2 star, G1 star G2 is the operation between G1 and G2, okay, like multiplication, addition, this is an operation. Now, in many contexts, when we have such a set and an operation, the result may not be in G. Right? For example, you can take division operation, and you can take two integers, and 2 and 3, and 2 divided by 3 is not an integer, it is actually a rational number. So, when you say a binary operation in G, we sometimes we mean that the result should also be in G, but sometimes it is not explicitly stated. So, we need that property for groups, that it should be an operation in G, which means its result also should be in G. So, this is the first requirement, that G comma star, a set together with an operation is a group if 1 G is closed under star. What it means is that G1 star G2 is also in G if G1 comma G2 are in G. For any G1 G2 in G, G1 star G2 is also in G. When that happens, we say that G is closed under star, meaning that if you have G, you take two elements, you multiply, or rather you take the star operation, it is still inside. So, it is closed under that operation. Now, 2, the operation is associative, which means that for any G1, G2, G3 in G, G1 star G2 that whole thing, the result you take star with G3 is same as you first what you get if you first take G2 star G3 and then take G1 star that result. Note that the order is the same G1, G2, G3, the sequence, the order is the same here and here, but the order in which we are taking the operations is different. Here we first take the first two and then operate it with G3. Here you take first, operate the second and third and then operate it with G1. So, they should be the same. This is called the associativity property. Okay. Now, third property is that there is an identity element. There exists an element called the identity element. We denoted by E or EG to be specific. Okay. Currently, we will write E in G such that E star G is same as G star E same as G for all G in G. Okay. Now, this is like for addition, this is like the 0 number, which if you add to any element any number, it does not change that number. Now, fourth property is that for every element for all G in G, there exists an inverse element, which we will call currently we will say there exists an H in G such that G star H is same as H star G, which is same as E. Okay. Now, this is often this H is often denoted as the G inverse is just a notation. Now, of course, before we can denote it that way, we need to ensure that such an H is unique, and that is indeed the case, and we will see that in a moment. So, these are the four properties that make a pair, this pair of a set and an operation in it a group. So, first of all we can check two very basic properties, that this identity element that we talked about, it is unique. There cannot be two elements having two distinct elements having the same property, satisfying the same property. Why is that? Suppose there are two elements, so E is unique. Why? Because suppose there are E1 and E2 in G satisfying the same property. Then what we know is E1 star G is same as E2 star G, and also this holds. Okay. And this holds for each of this E1 and E2. Okay. For E1 there is a H, and for E2 also there is an H, for which this product will be E2. So, one can now check that there is, because there is a inverse of G with respect to E1, one can just multiply by G inverse, or rather take the operation with G inverse on both sides, and what you will get is E1 star G star G inverse. Okay. We are not writing the order in which you will take the operation, because it does not matter due to associativity property. So, this is same as E2 star G inverse, and let us say G inverse here is taken with respect to it does not matter E1, and then what you get is E1 star E1 is same as E2 star E1, but because E1 is identity element, this gives us E1 equal to E2. Okay. So, E is unique, there cannot be two distinct elements. Now, very similarly one can say that G inverse is unique for any G. Now, why is that? Again, suppose there are two I mean G1 and G2 which satisfy this property here, then what we get is so let us call it H1 and H2. So, G star H1 is same as E, right, it is E, and which is also same as G star H2, because H2 is also an inverse, and then you can multiply. So, H1, so these both are inverses, and so we can take now multiply by H1 from the left, and what we get is H1 star G star H1 is same as H1 star G star H2, and this part is same as E also, because H1 is a left inverse as well, and that means E star H1 is same as E star H2, and then again it gives H1 star H1 is same as H2, a contradiction. Now, in both these proofs we have used a very simple technique, which basically says that if you have G star H1 equal to G star H2 in a group, it implies that H1 is equal to H2, and this we get by multiplying by G inverse on the left hand side. G inverse star G star H1 is same as G inverse star G star H2. So, this part is E, and E star H1 is H1, this part is also E, E star H2 is H2, and that gives us this H1 equal to H2. What it means is that effectively that you can cancel from both sides G and get H1 equal to H2. This process is the process of cancellation. Now, we have to be cautious here that you cannot cancel if G is on the left hand side here and on the right hand side here. So, it because G is on the left hand side on both sides, on the left on both sides you can cancel, but if we have G H1 is H1 H2 G, then we cannot cancel G from both sides, because we do not assume that the operation is commutative. Okay, now let us see some examples of groups. First of all, the set of all natural numbers. Is this an example of groups? Counting numbers, okay, or even the if you so clearly there is no element which you can add, which if you add it does not change the numbers. There is no zero element is not here. So, here there is no identity element. So, not a group. Even 0, 1, 2, 3 etc., the whole numbers, identity element is there, but there is no inverse. 1 does not have an inverse, 2 does not have an inverse. Okay. So, there is no number which you can add to 1 and it will give you 0. So, no inverse for non-zero numbers. If it is take any non-zero number here, they do not have inverse. So, not a group. but if you take Z, the set of integers which contains the negative numbers also, okay, integers under addition. Okay. So, I am not writing the operation to be addition here, but when we say G is a group, so when G star is a group, we simply write G is a group when the operation is obvious from the context. Okay. So, we do not always write this pair, we simply write G is a group, but what we really mean is that G together with that operation is a group, and the operation must be understood from the context. If it is not understood, then it does not make sense to talk about a set being a group. So, here when I was explaining this, I meant it is not a group under addition. Now, again this set of integers, this plus is a group. Okay. 0 is the identity element, and inverse of any n is minus n. Right, because minus n plus n is 0. Now, we can also take integers modulo any fixed integer. For example, let us take the number 8, we can take Z modulo 8, which is denoted by Z subscript 8. It is the set of all 0, 1, 2, etc. up to 7, and the operation is plus modulo 8. So, which means addition modulo 8, that is you add and then divide by 8 and take the remainder. Under this operation, this is a group. Z8 is a group. So, what is the identity element? It is 0. What is the inverse of 2? What is minus 2? Minus 2 is same as, there is no minus 2 here. So, what is the negative of or the inverse of 2? Okay, this is the inverse of 2. When I say minus 2, I mean inverse of 2. It is simply 6. 6 is there in this set. So, 8 minus that number is the inverse, because if you add them you get 8, which you divide by 8 you get 0, the identity element. Now, this is also, if you remember in our discussion on integers, this group can also be thought of as the set of residue classes, congruence classes modulo 8, that we denoted by 0, 1 up to 7. There are 8 congruence classes modulo 8, and the addition operation between congruence classes was defined as I plus j, these two congruence classes. So, what is this congruence class? Just to recall, this is the set of all integers which have residue 1 when you divide by 8. Okay. So, this is actually a set, each congruence class is a set of integers, infinite set of integers. So, this will have 1, 9 and so on, and the negative numbers also. So, I plus j, this is an operation between two sets, the two congruence classes. This was defined as I plus j, the congruence class of I plus j. So, if you take for example, the 4 plus 5, which is same as 4 plus 5, the congruence class of 4 plus 5, which is congruence class of 9, which is same as congruence class of 1. So, this is the operation, 4 plus 5 is 1. Okay. So, this is clearly the same thing as above here, because it is same as what is happening is you are adding here to get 9 and then you are dividing by 8 and taking the residue remainder 1. So, these two are basically the same groups, but just defined in slightly different ways. Now, another group that we have come across that we have not and that is, given a set S, we denoted by A of S as the set of all bijective maps, that is one-to-one correspondences, okay, and the operation is composition of maps. Okay. Now, so this is also a group, AS under composition is a group. So, what is the, so first of all it is clear that if you compose two bijective maps, you will get another bijective map. And what is the identity element? The identity element is the identity map of S, ID of S. So, it is a map of S to S and it is clearly a bijective map. Now, what is the inverse map? Because we know that every bijective map has an inverse, an unique inverse. So, that is the inverse under composition. So, we have already discussed this, that if a map is bijective, there is an inverse. So, that G composition F is equal to F composition G is equal to identity map. Okay. So, there is a inverse. So, this is a group. Okay. Now, particularly when you have S as a finite set with n elements and without loss of generality, let us suppose S is, let us not call it the set S, let us call it A as the 1, the 2 up to n, set of n elements, and let us say this, again A is a bad notation. So, let us take B and we take the A of B, that is the set of all bijective maps from B to B. Okay. So, this is a group and this is denoted by Sn, the set of all, basically this is a set of all permutations of these numbers, okay, permutations. A bijective map is nothing but a permutation of the elements. For bijective map from B to B is a permutation of the elements of B. So, permutations of B, okay, of n elements, and this is called symmetric groups on n elements or n objects. And this is a group, as we said, because it is just a special case of this, and there is a lot of structure in this, and this is a very well studied group, and we will also discuss it in some other time in more detail. Another very related group is the set of all invertible matrices of, let us say, you take fix an n and let us say n equal to 4 and take set of all invertible set of all invertible 4 by 4 matrices, let us say real matrices, real matrices with real entries. Okay. So, that is denoted by GL4, GLN in general, GL4 of R, real elements. So, R and 4 because it is 4 by 4 matrices. This is called general linear group. As you see, this is a group again. It is very similar because this defines 4 by 4 invertible matrices defined bijective maps of R4 bijective linear maps. Okay. So, only difference from before is that they are still bijective maps, but they are not all bijective maps of R 4 to R 4, they are bijective linear maps of R 4 to R 4. So, that is why the term linear. Okay. Now, as we have also noted that this is noted in a previous class, that this is a non-commutative group. Okay. So, if a group is if the operation if so it's if star is commutative operation, then G is said to be a commutative group, commutative or abelian group. Okay. So, this is the definition of abelian group. Now, what we discussed here, Z8 is an abelian group, Z is an abelian group, and however, these groups defined with using bijective maps, whose elements are bijective maps, these are all non-abelian groups, AS in particular Sn, and then also general linear group, these are non-abelian groups. So, there are many more abelian groups, for example, the set group of rational numbers under addition, this is a group. This is the set of rational numbers. Similarly, you can take the set of real numbers also, this is a group. These are all abelian groups. You can take the set of complex numbers with addition, these are groups. In all these elements, in all these groups, the number 0 is the identity element. Okay, we have seen the definition of groups and some examples. Now, we will continue further on properties and further theory of groups. First of all, a very simple observation, you should note that if we have two elements G and H in a group, then if you take GH, which is G operation H. So, G is a group, so it has an operation. We are not explicitly writing the notation for the operation, but it is understood that whenever we say G is a group, there is an operation that we are not mentioning. And when we write GH side by side, we mean that G, that operation H. So, if the operation is denoted by star, this actually means G star H. So, in commonly we do not even mention that operation star, we just write GH to mean that it is G star H. So, GH inverse, this is H inverse G inverse. Okay. How do you see this? We simply multiply GH with this and see that it will be the identity element. Why? GH times H inverse G inverse, this is equal to, you can use associativity to rearrange the order in which you will do the multiplication, or rather the operation. So, G H H inverse G inverse, and this step to this step requires several use of the associativity property. Actually, you have to first take G. So, maybe one of them you can break, you can do GH H inverse G inverse first, and then you can further use associativity here to write it as G H inverse and then G inverse here, okay, and this is what actually I have written here. Ideally it should be written this way. So, G times the identity element E times G inverse, which is G times G inverse, so which is identity, right. So, this means that this is the inverse of G H, that is this. Now, whenever G is finite, this denotes the size or cardinality of that finite set, and that is called the order of the group, order of G, and often denoted by either this or this notation. Now, if we have a subset of G, if we have a subset H of G such that H is also a group under the same operation, then we say that H is a subgroup of G. Okay. So, the same operation is important. We do not mean that you can define some other operation in H and then H is a group under that operation. Then it is true that H is a group under that operation, but it is not the same operation as the operation in G. So, H will not be called a subgroup of G in that case. If under the same operation as in G the subset forms a group, then we say that H is a subgroup. So, let us see some examples of subgroups. We know that Z, set of integers under addition, is a group. So, we can take n Z, n multiplied element wise to every element in Z. Okay. This is actually a set. It is defined as n times I, where I belongs to Z, this set. Okay. You can see that this is a subgroup of this Z. Okay. So, whenever this is H is a subgroup, we often write in this notation, H less than G. Okay. This is a subset notation, but if you say less than, it means that it is a subgroup of G. Now, so this is a subgroup of G, this is the claim. Okay. So, you can see first of all that 0 is there in this, 0 is the identity element in Z, it is there in Z in this set also. You take any two multiples of n. So, this what is this set? This is the set of all multiples of the fixed integer n. So, for example, you can take n equal to 8, then this is the set of all multiples of 8, 8i, where I belongs to Z, right. So, clearly 0 is a multiple of 8, 0 is there, and if you add any two multiples of 8, you will get another multiple of 8. So, 8 times I plus j, this is a multiple of 8. Now, similarly, you can also see that any multiple of 8, its negative minus 8i is also there in that set. It is also a multiple of 8, because it is 8 times minus I is also in Z. So, this is also there in this set of all multiples of 8. So, this set has all the properties of group under the same operation, which is the simple addition operation. So, this is a subgroup of this group. Now, let us take we know that set of all real numbers under addition is a group. You can see that Z is a subset and it is also a subgroup, is a subgroup. In fact, set of all rational numbers, this is also a subgroup. Right. Now, take R2, we know that under component wise addition it forms a group. What is this R2? It is the set of all pairs of real numbers x, y pairs, where x, y belong to the real set. This is a subgroup. Now, now if we take, so this is the real plane actually, set of all vectors, two dimensional vectors. Now, if you take the only the x axis, it is a subset of this real plane. So, what is the x axis as a set? You can write this as x comma 0, where x belongs to R. You fix the second component to be 0, then you get the subset which corresponds to the x axis. If you take the set of 0 comma y, y belongs to R, this corresponds to the set of set y axis, and both of these form a group, form a subgroup of, these are subgroups. These are subgroups, okay, both of them. Now, it is very easy to check that, because you take any two vectors in the on the x axis, you get another vector on the x axis. There is a negative vector of something lying on x axis is also on the x axis, right, and so on. So, same thing holds for the y axis also. And not only this, you can actually take any line going through the origin, this set. So, in other words, you can take say any slope, you can take, for example, you can take 2 here and 1, and this set then is denoted by some multiple of 2 comma 1, okay, where lambda is a real number. Take all multiples of the vector 2 comma 1, this is the subset that corresponds to this line, right, and this is also a subgroup. Now, let us take another example. Take any group G and any element G in it, and let us take the set which we denote by this symbol. We will see that this is, we will say this is the subgroup generated by that element G. It contains all the elements of the following form: G power n. Now, what do you mean by this? N belongs to Z. Remember, Z has actually nothing to do with G. G may be a group, it is not a subgroup of Z or anything. So, Z is just the set of integers here. So, G n is defined as, G n is defined as G times G times G. So, times means it is the operation in G, right, dot 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 G n times, if n is positive, n greater than 0. It is the identity element if n is equal to 0, and it is, if it is negative, what is its definition then? Suppose G power minus 5 we say. What is G power minus 5? So, we know that G is a group. So, there is G inverse in it also. G inverse is also an element in G. So, what we do is we take G inverse times G inverse times G inverse n times. not n times, minus n times when n is less than 0. So, if n is negative, then minus n is positive. So, we take minus n times operation of G inverse with itself. That is the definition of G power n for n negative. Okay, so we have defined the power n for any integer power for any element in the group. Now, we take the set of all such powers of G, that you can check that it forms a group. So, it is very easy to check now. Clearly E is there, the identity element is there in it, it is closed, this set is closed under the operation. Why? Because you take any Gn star Gn, you can check, sorry, Gn times Gm, you can check that it will be G power n plus n. Okay. You can take various combinations of n positive, m negative, n positive, m positive, and all these cases, and use the definition of Gn here and show this quite easily. And the inverse, existence of inverse is quite obvious, that is because you take any element Gn, G power minus n is the additive inverse, because we, as we have said just now, this star this is equal to G power n minus n, which is G power 0, which is the identity element. Okay. Of course, this needs to be proved using the definition. Now, so this forms a group, subgroup, this is a subgroup. So, G is a subgroup, this is a subgroup, and this is called the subgroup generated by G, and we will give a more general definition of a subgroup generated by any subset of elements. Okay. So, we will continue our discussion on groups. So, if we had given two groups G and H, let us say G star, star is the operation in G, and in H the operation is, let us say, this circle. If you are given two groups like this, then G cross H, you know, if you have two sets, then the Cartesian product is defined, is denoted by G cross H, and the set is indeed G cross H, the Cartesian product, but the operation is component wise. So, its elements are G comma H, where G is in G and H is in H, and the operation is defined as, you know, G1 comma H1. Let us denote the new operation as this symbol hat, G2 comma H2. Okay. This new operation is defined as this G1 star G2 comma H1 circle H2. So, it is not necessary to, it is not necessary that these G and H are similar sets. For example, both elements of both these sets are integers or real numbers which can be operated on. There is no operation defined between elements of G and elements of H here. So, the operations can be quite different here and here. Okay. So, operation between the pairs of elements is simply defined component wise. This first element here, there is an operation between them which is defined in G. So, use that. Between the second components, again there is an operation defined in H, use that for the second component. That is how the operation between the pairs is defined. So, of course, we are very familiar with this type of operation, the product operation. For example, in R2, we commonly talk about R2 and we define vector addition. How do we do vector addition in R2? R2 is exactly the set of all real numbers like this x, y in R. So, what we have done here is this is R cross R, and R is a group, okay, and the operation is defined as x1 y1 plus x2 y2 is exactly x1 plus x2 comma y1 plus y2. So, you see that here the operation is indeed defined in the way that we defined here, and this is called, this definition G cross H is a, in fact can be checked that it is a group under this operation in general. So, if we are given any two groups with their respective operations, you can define a product group, it is called the direct product of H, G and H, where the operation is defined to be component wise. Okay. So, this is the direct product. And when we take R2 for example, this is exactly the direct product of R with itself. So, you can take direct product of any number of groups. For example, if you have G1, G2 etc. up to Gn, you can define direct product G1, G2 cross Gn. Again the operation, so these are n tuples with elements from the ith element is from Gi, right, and the operation is defined for the ith component according to the operation in the ith group here Gi. Now, if the groups are the same here, these groups are the same, then you say that it is Gn. Gn is the direct product of G with itself n times. And so, indeed we are familiar with Rn, Cn, Zn and all these things. So, any set power n, we actually naturally define operation in those sets by defining them component wise, doing component wise operation. So, this is the direct product. Now, let us come back to, for simplicity, let us just take two groups and their operation. Clearly, if you take the subset E G, now because there are two groups, we talk about identity element, both of them cannot be denoted by the same symbol E. So, we now subscript it with E G and E H to denote that it is the identity element of G, this is the identity element of H. So, if you take E G comma H, where H belongs to H. So, what we have done here is that we have fixed the first component to be the identity element of G. Second component now is free to be taken from H. This is a subset. So, this is like the y axis in the case of R2, we are saying the first component is fixed to be 0. So, it is 0 comma y kind of thing. So, it is the kind of set. So, it is the y axis. So, this is, as we said, in this case this y axis was a subgroup. So, similarly here also you can easily check that this is a subgroup of G cross H. Okay. And similarly you can also fix the second component E H, where G is free to be taken from capital G, and this is also a subgroup. Okay. Now, let us study subgroups a little more and what it gives us. So, subgroup, as you said, is a subset of the group, but it has a nice structure. So, this is G and this is H, it is a subgroup. Now, let us take the example of NZ to understand something. Okay. So, NZ. So, particularly take, let us say n equal to 8, and so 8Z is the set of all multiples of 8. Okay. So, 8I where I belongs to Z. Now, we know that there are these congruence classes of 8. Okay. So, they are obtained by adding 1 to this whole set, adding 2 to this whole set, adding 3 to this whole set, and so on. So, which means we take 1 plus 8 z, which is set of elements of the form 1 plus 8 I, where I is in z, 2 plus 8 I, 8 z is 2 plus 8 I, where I is in z, and so on up to 7 plus 8 z, which is 7 plus 8 I, where I is in z. Okay. So, these are actually the congruence classes modulo 8, right, because you divide each of these numbers, you get 2, they have the same remainder. So, divide and you get the remainder 2. So, they have the same remainder when divided by 8. And we have discussed these elaborately before. So, now this set forms a subgroup. Does this set form a subgroup? No, because you can see that if you add 2 elements of this form, you will get an element here, because this 1 gets added 2 times. So, 1 plus 8 and 1 plus 16, if you add, you will get 2 plus 24, which is in this set, 2 plus 8 z set. So, it is not closed under this operation, addition operation. So, it is actually not a group, and also 0 is not there in this group. So, but this is, you can think of this as the shifted version of 8z, right. If you look at the set of integers z, you have 0 here, you have 8 here, you have 16 here, minus 8 here, and so on. And what is this 1 plus 8z? It has 1 here, 9 here, 17, minus 7, minus 15, and so on. And this set is further shifted version, it is minus 14, minus 6, 2, 10, 18, and so on. So, these sets are basically various shifted versions of this set, and these sets are called the cosets of the group 8z. So, you have one subgroup which contains the 0 element, of course, and its shifted versions. Okay, these are called cosets. So, these are cosets. Now, of course, this group Z is an abelian group, meaning its operation, addition operation is commutative. Now, if you do not have an abelian group, the operation is not commutative, then when you add 1 or any element, one has to either say add or not add really, I mean that do the operation from with 1, then you can do the operation either from left or from right. They are different, they need not be the same thing, like here addition is commutative. So, it is the same thing whether you add it from left side or add it from the right side, but if the operation is not commutative, then the operation can be different if you do it from the left or from right. So, we now talk about left cosets, which is obtained by, so first of all you are given a subgroup H of G, and then we take an element G in G, and we define G H. Now, there is an operation here actually, but we denote it by G H. It is denoted by G star H, where H is taken from H. So, you take every element in H, operate it with G and take the outcome. Okay. So, all those outcomes are taken in a set. This element is fixed. You fix an element G and operate it from left side on each element of H. So, you have this H, you fix an element G, take G times H for every H here, and then you get another set here. That set is denoted by G H. So, when you operate G from left, to all the elements of H. Similarly, you can take another element, operate it with all these elements from left, and then you get another set like this. These are called cosets. What we will see is that these cosets are actually disjoint. They do not have any intersection, and they form a partition of this whole group, and all of them have the same number of elements. You have seen these features here, that these cosets, there are exactly 8 cosets here, and they are disjoint sets. Their union is the whole G, and you can see here it is an infinite set. So, it is not right to say that they have the same number of elements in the normal sense, but you can see that there is by shifting one set you can get another set. So, in that sense they have the same number of elements. So, this is what we will see for finite groups. This will happen, that there are the same number of elements in each coset, and in fact, we will in general prove that there is a one-to-one correspondence between these cosets, and they partition the whole group. So, another way to view these left cosets, whatever we are talking about left cosets, similar things can be said about right cosets also, okay. But we will just restrict our attention to left cosets for development of, for understanding the intricacies. So, another way to look at left cosets is the following. We can define a relation, just like here we defined a congruence relation modulo 8. We said that two integers are congruent, I is congruent to j modulo 8 if 8 divides I minus j, right. And under this relation, and we have seen that this relation is an equivalence relation, and this gives equivalence classes. And what are those equivalence classes? These equivalence classes are these. These cosets are the equivalence class. Cosets of this subgroup 8z are the equivalence classes for the relation which is congruence modulo 8. For this relation, for this equivalence relation, the cosets are the left, the equivalence classes are the cosets of the group 8z, subgroup 8z. We will see a similar thing. We will, in general, for any subgroup H of G, we will see that those left cosets are actually the equivalence classes for some equivalence relation. So, what is that equivalence relation? The equivalence relation is called congruence modulo the subgroup. So, here we said congruence modulo 8. You can, here we are saying basically in this case it will be congruence modulo 8z, the group 8z. Okay. So, what is congruence modulo H? We say that if you have G1 and G2, two elements in G, we say that they are congruent modulo H. If, so G1 is congruent to G2 modulo the group H, if G1 H1 is same as G2 H2 for some H1 H2 in H. Okay, so, there is some H1 and there is some H2 in the subgroup such that G1 H1 is same as G2 H2. Now, there is another way to look at it. If this happens, and this is in fact if and only if G1 inverse G2 is, you take multiply by G1 inverse on both sides from left, and then by H2 inverse from right, then you get H1 H2 inverse, and this is in H, because both of them are in H. So, what we are saying is that G1 inverse G2 is in H. This is the condition. We say G1 is equivalent to G2, congruent to G2 modulo H if G1 inverse G2 is in H. Now, this is very similar to the definition of congruence modulo 8. If you see, how did you define it? We said I minus j should be divisible by 8, which means I minus j should be in the subgroup 8z. It should be a multiple of 8, and minus j is exactly the inverse of j. So, we have actually taken I operation I plus minus j, I plus minus j is in the subgroup 8z, and this is how we are doing here also. We are taking G1 inverse G2 is in H. Okay. And same way, this also means that you can take the inverse of this, because H is a subgroup, its inverse will also be in H. So, which will be G2 inverse G1 is in H. So, it is the same thing. So, I minus j or j minus I, both of them will be in Hz. So, this is a generalization of the definition here, this relation. Okay. And under this relation, we can see that this the equivalence classes, this is an equivalence relation. So, this relation congruence, let us say this is the lemma, congruence mod H is an equivalence relation. It is very easy to check. Let us check this. First of all, what conditions do we need? Equivalence relation means reflexive, that means you take any g in G, G should be related to itself. Now, what is the definition? When do we say it is related to itself? G inverse G here should be in H, but what is G inverse G? It is the identity element, and it is in H because H is a subgroup. The identity element must be there in H. It should be symmetric. What does it mean? If we take G1, G2 in G such that G1 is related to G2, which means G1 inverse G2 is in H, then we know that its inverse is also in H because H is a subgroup. So, G2 inverse G1 is also in H, and that means G2 G1, G2 is also related to G1, right. Transitivity, what do we know? G1 is related to G2, so G1 inverse G2 is in H, G2 is related to G3, so G2 inverse G3 is in H. These two together implies that their product is also in H, means their operation between them is also in H, which means G1 inverse G2, G2 inverse G3, which is same as G1 inverse, this is identity element, G2 inverse is identity element, right. So, it means G1 inverse G3 is in H. Their product should be in H. So, this should be in H, and G1 inverse G3 is in H. That means now, which means that G1 is related to G3, it is congruent to G3 mod H. So, these three conditions are satisfied. So, this is an equivalence relation, and it will give us equivalence classes. What are those equivalence classes? Those equivalence classes are exactly the left cosets of H. And to see this, let us write down the equivalence classes. What is the equivalence class? So, equivalence classes under this relation. You take any element G in G, you fix it, and let us see what is the set of elements in G to which this G is related. Okay. So, I want to find what are those elements G1 with which G is congruent to, what is the set of, G1 such that G is congruent to G1 mod H. What is the equivalence class of G? This is the equivalence class of G. Let us call denoted by this, and now what is this? This is G1 such that G inverse G1 is in H. That means, these are the elements for which G inverse G1 is equal to small h for some h in H. Right? This is an element in H, which means it is equal to H for some H. Now, that can be also written as this implies, this means that G1 is equal to, you multiply from left by G, what you get G1 equal to GH. That means, it is the set of all GH, G1 is equal to GH, right. So, you can replace G1 by GH with H belong to H. So, every element in H you multiply from left by G, multiply rather do the operation, left operation with G, and that gives you the set of elements to which G is related. So, what does it mean? It means that we have this G, you have H here, and you have an element G here, anywhere, it can be inside H, it can be outside H. You do left operation with every element in H and you get a set, and that set is this set, because it is the left coset of G, it is GH. Okay. And that is the set of elements to which G is congruent to modulo capital H. Now, the way I have drawn it, this G itself belongs to GH, and that is true because GH has the identity element also. So, G times E is also there and it is equal to G. So, G is also there in that left coset. Okay. So, any element, its equivalence class is something here, and we know that equivalence classes partition the whole set for any equivalence relation. So, these are disjoint sets whose union is the whole set G, and these are exactly the left cosets. So, okay, so what we have done now is that we have seen that left cosets can be seen as equivalence classes under this operation congruence modulo H. They partition the whole group.